Okay, so last time I started talking about using value function approximation in order to represent a value function. This is important when we have, say, a problem with a very large state space that we cannot represent the value function exactly. And I talked about some general ideas about value function approximation, talked about approximation error, a little bit about estimation error. We had that kind of piecewise constant example as just the simplest example of function approximation. So the goal of today is talk about several ways that we can try to compute the value function using a value function approximator. So this is the scenario that we assume that we even know the model, for example, but we cannot represent the value function exactly. So the question is that how we can find that value function or compute that value function. So I start from the setting that the model is known, as I said, and later we get to the point that when the model is not known and we are in the full reinforcement learning setting where we only have data. But many of those approaches are essentially a sample-based version of the approaches that I'm going to talk today. And you will see that the change would be kind of minimal and also expected. I don't get to that point, so that I will continue talking about the learning part next time. Okay, so just let me. So we talk about population version of these approaches. So population, and in many cases, these approaches are defined based on some loss function. And as you probably know, population loss function is when we have the true distribution. So just kind of giving you an example, if we have a loss function, say, which depends on some x and some function. So for example, if it is, and maybe y here for the case of regression. So if we have f of x minus y squared, this is the usual loss that we use in regression. What we minimize would be like summation of this over all data points, so xi, yi, f, and then we minimize this over f. So this would be like empirical loss, you sometimes call it. And the population version is when we have the expectation, when x and y is coming from, say, the true data distribution. So this is the population version. And I'm going to talk about these type of loss functions or methods. Sometimes they're not necessarily loss function. And then, as you see, if we know how this population loss function is, in many cases, we just go from this population version to the empirical one by just substituting expectation with some summation of the data. So understanding the population loss is going to be useful. So let's kind of have some reminder of some notation that I'm going to use on norms, LP norms. So these are similar to probably the usual LP norms, that norms of vectors that you have seen. We can just define them also for functions. So how do we define them? So we say that, okay, so suppose we have a probability distribution nu that belongs to some space of, but it's a probability distribution, so it belongs to space of distributions defined over that domain. So here I'm writing it as X because we use X for states, but it can be any space domain that we are talking about or we want to define. And then we have a function, value function V. In general, it's not necessarily value function, but it can be anything. Then the LP norm of V when P is between 1 and infinity is defined this way. If it is smaller than infinity, so it's not infinity, it is defined as this expectation or integral that LP norm of V with respect to distribution nu, just to the power of P, I hear it so that I have a simpler formulation, would be V of X to the power of 2, power of P, and weighted according to that probability distribution nu. So this is the LP norm. Usually, probably what you have seen before would be something like this. So for example, if we want to write it, so we could define it, well, the norm like this, L2, that would be L2 norm. So here we have d of x, so it's kind of integration over the domain, and that would be essentially of the same type when nu is having specific form. It is when it is having some kind of like uniform weight over all states. So you have probably seen this integral form, but here I'm talking about, I want to be specific about the distribution. So nu here, I may change other distributions, nu rho, to emphasize what is the weighting function that I'm using. And in most of this lecture, and I think the rest of the course, we will talk about L2 norm. So we just have, okay, I guess for some reason it doesn't recognize my palm. So we will have L2 norm of it. And if it is clear what distribution we are talking about, like here instead of mu, I may just drop the distribution. Okay, so this is clear, right? And then we have L infinity norm or supremum norm, which is defined essentially the way that we had seen it before. We just go over all states or all x's and take absolute value and take the supremum over that. So that's a maximum value of a function. So I guess that's what I want to say here. If I want to emphasize in some cases that distribution is defined over state space, so it's defined over X and not state action space, not X and A, I may use a subscript of X to emphasize that. So I write it nu of X, and then the norm would be like this. Okay, so the first approach, now we know about the norms, let's talk about how we can find a value function within some function space F. So your function space might be a neural network, it might be a piecewise constant function, it might be decision trees or anything. Here I want to abstract away from the specifics of the function space for now and talk about the general principles. Later I'm going to talk about some specific examples. Okay, suppose we happen to know V of pi, or Q of pi, or V star or Q star. Suppose we know them. Some oracle gives one of these to us. And we just want to represent it with a function V within that space. So basically our goal would be to find a V, finding V in that function space, such that V is approximately equal to V pi. So that's essentially what approximation means. So how can we do that? So if I give you V pi and I give you a function space F, how do you even define being approximately close?
Empirical risk minimization.
Okay, but it's not, yes, but this is not the empirical. There's no data here.
No, okay.
So how do you define it?
Use the norms you just defined.
Okay, yes, exactly. Like I can define a norm, and what do I do after choosing the norm?
To get the metric space, you have to subtract the values at the inputs,
Okay.
and then feed that to the norm.
Okay, yes, and then minimize it over the function space, right?
Right.
Okay, so that's a basic idea. It's very simple. So we have to quantify what it means for v to be close to v pi. So I use approximate symbol, but we need to make it something that is easier to compute. So we define a distance function between functions. So we define a distance function, so d, which takes, say, two functions and then return a real valued number. And then given such a distance function, we can try to find a function that minimizes that distance function. So if we can write our objective as minimizing over all value functions in that f, such that the distance between v and v pi is minimal. So maybe some mental images would be helpful. I think this is clear, but some mental images would be helpful. Maybe if the function space is linear, so we can usually show it with a plane to visualize it. So if this is our function space is like this two-dimensional plane, I'm showing it. And suppose there is this point, which is v pi. So I want to represent one function here that has minimal distance. So essentially, I find a point, v here, that this distance function is minimized. In general, v of pi is not inside or within that function space f. It might not be representable in that space. So that's why when we visualize it, we show it outside that space. So that's one way. So this is showing function space as a kind of plane. In some other cases, it might be kind of more clear to show it something like this. Say if this is the value function space, so I show you as a ball maybe. And then this is v of pi. And then still we are trying to find the minimum distance. So here, this f is like the, you can think of it as an image of some nicely shaped function space. So for example, it's a convex set of some functions. So I'm bringing these things because we will see these kind of images or visualization later. So it's good to be clear. So here the idea is, again, to find a point that has the minimum distance. Either I show it this way or with a plane.
Sorry. Can we think of the two, for example, like normalized version of these two functions as two probability distributions, and then use something like, for example, KR divergence to minimize the distance between them?
Right. So yes, okay, so I think what you're saying, if I understand correctly, is that you convert these value functions to some distributions in some sense by somehow normalizing them, and then use a distance which is defined for distributions like KL distance in order to find a minimum of them.
Yeah.
Okay, so it is possible. Like here, I haven't specified how you have to choose that distance function. It can be anything. If you do that, basically you're doing one mapping to probability spaces, and then one mapping. Another step would be to define a loss function there. That is, I think, in principle possible, but there are a lot of other like distances that are directly defined on the functions that we don't need to have this extra mapping.
Okay, I see. Thanks.
But that's in principle possible. What happens, what properties you have, is to be seen. So later we will see in more, or maybe I'll briefly mention in policy gradient type of methods or policy search type of methods, the methods that try to minimize the distances between policies based on something like KL divergence is more common. But that's because policies already have some kind of probabilistic interpretation already. I mean, there are probability distributions. So here, let's define one common family of distances. They're based on LP norms that I just defined a few slides ago. So essentially, we choose an LP norm with respect to some distribution, probability distribution mu, and then try to minimize the distance based on this norm. So we find a v in function space such that the distance v minus v pi, according to this LP norm, has the smallest magnitude value. And a common value that we choose is, or common LP norm that we use is L2 norm. So it's not any p, but just p equal to 2. And this should remind us of the mean squared loss function that we commonly use in regression. So I had it a few slides ago. So for example, here at the top, we essentially have squared error. So this is L2 norm between samples or out targets and our function. So we are essentially doing similar thing. We can do similar thing here if we choose L2 norm. Okay, is there any question so far?
Hey, Professor. Is there a situation where you would use like something that's not L2? And I mean, aside from L1 and L2, normally I would see like in most machine learning courses, it's either L1 or L2, right? So is there a situation where you would use something else?
There are, but they're not, as I guess as you observed, they're not very common. One case that some people use in machine learning in general, maybe less in reinforcement learning, is some form of robust loss function. So the problem with L2 is that it is sensitive to outliers.
Yeah.
So if you have a value that is very different from others, from other values, okay, so maybe just
it explodes. Yeah.
Yeah, so it moves everything away. So L1 helps it a little bit, but there are all sorts of other loss functions that are less sensitive to outliers. So if we believe that we might have outliers in our data set in some way, there are some other loss functions that can be used, like Huber loss function. In reinforcement learning, and people have explored many loss functions, but they are not very common.
Okay, thank you.
Okay, so here I started from saying that suppose we have access to V pi, but how can we even have access to V pi? That's a problem that we want to actually solve, right? Finding V pi. And if we know it, what is the reason for approximating it after all? So that's another question that you might ask. I'm going to say that, well, these are valid points, but first I'm giving you a way that you can have access to V pi, or at least a noisy version of it, without knowing it for every point, like without having an oracle that giving you V pi. So one option is to use Monte Carlo estimate. And if you remember, Monte Carlo estimate was that we essentially start from state X, say, and then we follow policy, and we compute the return. And maybe we can do it several times. That was one possibility, or just one time. And each of these, by following a policy, so this is going to return 1, return 2, trajectory 2. And if we added them, the average of them would be an unbiased estimate of the value function. So for states, so this kind of gives us this recipe, similar to what we had before. At state X, which might be belonging to some high-dimensional space, continuous space, we follow this trajectory, Monte Carlo trajectory, and what we get out of it is a value function that is contaminated with noise, only at that state. But the good thing is that the noise is zero mean, so it's unbiased noise. So we don't get the value function, but we get a noisy version of it. So I guess that's one thing. Like, it's a procedure for getting V of pi, a noisy version of it at one state. If the state space was small, like finite and small, like 1,000 states, million states at most, so something like that. I don't want to give a specific number because in a few years people say that, oh, million states is nothing. So, okay, billion states for the next generation. We can run Monte Carlo estimate for all states. But then if it is continuous, like an infinite number of, uncountably infinite number of states, we can't do that. Just as another reminder, in Monte Carlo, in previous lecture, in Monte Carlo, when we talked about Monte Carlo, doing policy iteration with Monte Carlo estimation, so we actually went through over all states, if you recall, in one of the methods, and compute this Monte Carlo estimate for all states. This is not possible in continuous state spaces. So what we can only hope is that if we have a state space like this, we only have a Monte Carlo estimate for some of the points. So each of these is kind of one trajectory I'm showing you. So we have the noisy estimate of the value function only here. Now, this is one of the other roles of function approximation, is that it helps us to generalize. Because if we fit a value function to these values that we get here, and then this value function approximator can help us, or can give us an estimate of value function at any other query point. Like if you have a query point here, or here, or here, it will give us some example after finding that function. So this is what we do essentially, like supervised learning a lot. Like we only have a finite number of data points, but the hope is that we can generalize over the whole state space. When it is possible, it depends on many factors, like whether the function is behaving nicely or not, whether it is continuous or smooth, or it's very discontinuous. So that's why some problems are easier to learn and some problems are more difficult to learn. So yes, I guess that's a kind of the point here. Even if we don't have V pi, we can find estimates of it at certain points, and we can use the function approximate to generalize over the whole state space. So that's generalize. I think, yeah. Is there any questions on this?
I have a question. How important do you think is the initialization of the function, the approximate function?
Initialization in the sense that, like, say, we do in deep neural networks?
Yeah, for example.
Right. I mean, here I'm not talking about how we find, okay, so essentially when we have this minimization here what I'm writing is just find global minimum of that. And I'm not talking about how optimization should work. But when in practice, or when you work with something like deep neural network, then the optimization point also matters too, which means that if your initialization is bad, you may not find a good solution for this minimization problem. So say if you have a kind of like loss landscape. So this is your loss function. It's a function of f. So it's kind of like a very abstract visualization. This is your, say, global minimum. But if you start from here, you may fall within that local minimum. And then the question is that how worse this local minimum is compared to the other one. But of course, I mean, there are all sorts of results in deep neural network literature that says that, I guess there are two things. One is that many of these local minimums are not actually too different from each other. So that's, I guess, one type of methods. Like, we don't really need to find a global minimum. It is enough to find because many of the local minimums are actually good minimum.
Right.
Sorry, go ahead.
I was thinking of the case with finite, when we know the ground truth V for a finite number of states. Like, even if we found the global minimum, the exact behavior of the function approximation, intuitively, I feel like it would be very dependent on the initialization.
Well, if you find a global minimum, and it is, say it's a unique global minimum, then if it is unique global minimum, then doesn't matter on initialization, because you always find the same point.
Okay, thanks.
But if it is local minimum, or it is not unique global minimum, then it depends on your initialization.
Sounds good.
Okay, any other question? Okay, so let's talk about another approach. So here, that was a kind of oracle version giving us V pi. We can do it with Monte Carlo estimate for some points, but let's think about other methods that don't need V pi at all. So here we want to do something similar to value iteration, but just make it approximate. So I want to talk about approximate value iteration. And as you recall, value iteration is kind of like one of the main algorithms in RL, and methods such as like Q-learning would be kind of a sample-based version of value iteration, as we saw before. So recall that value iteration is this iterative procedure that we get Vk, apply the Bellman operator T to get Vk plus 1. And T is either the Bellman operator for pi or Bellman optimality operator. So I use T for both of them here. So one way to develop an approximate value iteration is to perform each step only approximately. So find a V, Vk plus 1, that belongs to function space F, such that it is approximately equal to T of Vk. So that's a general idea. And we can, again, define a distance function to define how the closest, this approximate symbols, to quantify that approximate symbols, we can define different distance functions. But a commonly used one is some LP type of norm, and most commonly actually L2 norm. So what we have here is we find Vk plus 1 by minimizing our function space F, a value function that is closest to tvk in the sense of LP norm, which is weighted according to some distribution mu. So we find the T, I guess we can see it like this. Yeah, maybe I can, if it's a linear function space, we start from some Vk within that space. Vk is already in that space. We apply the Bellman operator to it. It may go out of that space. So I show you like this point. So that would be T of Vk. And now I try to find a point that has the minimum distance in that space. So for example, I find the orthogonal projection of it, which would be the minimizer of the L2 norm. And if we do that, that would become my Vk plus 1. And then I may apply this again. I get T Vk plus 1, each again might be outside that space. And then I compute Vk plus 2 here. So at each step of this procedure, we are solving an optimization problem. And the solution of the previous optimization problem would be the value function that we now apply the Bellman operator to it. Is this clear?
Sorry, why are we assuming two different spaces for the approximate functions and the actual function after Bellman operator?
So actual function in the, so there is only one space for value function approximation, and there is another space which is the space of all possible functions. So maybe I should be more clear here. When we have a VK here and I apply it and gets tvk plus 1, it goes to a superset of that value function space that we have. And that superset is a space of all possible functions that we can define over that domain. So maybe a mental image here would be this one. So when we have a piecewise constant approximation, this blue curve here, okay, this blue curve here is one function in that outside space. It's any function. So it could also be some function like this. But then these green functions that are defined by these piecewise constant values are the functions within that function space F. So these are only things that we can represent. But there might be, after, and actually I guess this is a good point, after applying the Bellman operator to a function within that space, it may go out of that space. So yeah, let's try that actually. Did it solve somehow? Clarify a little bit?
Yeah, so my understanding is that we want a subset of the actual function space purely because of the convenience of optimization.
Because we cannot represent, yes, exactly, because we cannot represent, so the exact representation of arbitrary function on RD is impossible on a computer. That's why, yes. Okay, so we are here. So, but I think your point is good to try to come up with some simple scenario that show this point, that so even though value function might belong to some function space, after we apply Bellman operator to it, it may not belong to that space anymore. So yeah, so let's try to show it. I'm trying to find a very simple example. Suppose we talk about a very simple MDP, and I'm talking about just a policy evaluation, so there's no action. So we have two states. So state may be x1 and x2. So this MDP works like this. So when we are at x1, we go to x2, and when we are at x2, we go to x1. So it is, and the reward that we get here is 1 for x1, and reward 0 at x2. So this is kind of like we go to x1, get reward 1, we go to x2, we don't get a reward, and then we come back. And suppose, oops, we have a gamma factor, so it's a discounted problem. And so the reward function can be written as a vector, right? So what would be the vector? So it's 2 by 1 vector, right? Because we have two states, or 2 by 1 matrix, or two-dimensional vector.
1 and 0.
1, 0. Okay, so that's good. So I write P down here. So what is P? So it's 2 by 2 matrix.
Sorry, in this way, this seems like a stochastic process rather than a Markov decision process.
Yeah, it's a kind of Markov reward process. It's called Markov reward process because don't have any action to choose. But you can think of it, you have an MDP, and a policy always chooses one specific action there, and now we want to evaluate that policy. So policy, so this is still within the framework of MDP that we have, and the goal is to compute V pi. So what would P? Would be P? Any idea? Maybe in chat?
1001.
1001, this way?
Would it be the opposite, like
Yeah.
0110?
Okay, say again, please.
Like 0110, so that whenever you multiply your state into it, it'll keep switching.
Yeah, exactly. That's true thing. Like from state 1, so this is state 1, with probability 0, we go to state 1, with probability 1, we go to state 2, and vice versa. So let's see what's the value function for this. I mean, this is, okay, so value function of, okay, so essentially what we have is that value function, which is two-dimensional vector, in the exact case, would be reward plus gamma p pi. So it's a Bellman equation, which if we write it down, I think it would be v of pi of x1 is 1 plus gamma of x2, right? What about v pi of x2? What should I write?
0 plus gamma times v pi x1.
Yes, exactly. So v of x2 is gamma times v of x1. So I think if I substitute here, I get 1 plus gamma v pi of x1, which means that, sorry, there's a mistake here. It should be gamma squared. So 1 plus gamma squared, so v pi of x1 would be 1 divided by 1 minus gamma squared. And v of pi of x2 would be gamma times 1 minus gamma squared. Right? Okay, now suppose, so this is the true value function. So it's a vector with this specific form. Now the question is that suppose we want to use a simple function approximator, and the function approximator that we use is assigning the same value to both states. So I can write it as, so function approximator, I have it as v of x equal theta. Okay. So this means that if x is x1, it gives theta. X is x2, it gives theta. So this is a function, this is like piecewise constant, but there's only one piece. And suppose we start from v equal to 0. Suppose, okay, so at v iteration k equal to 1 or 0. So we start from v0. And suppose we choose theta to be equal to 0. So at states k iteration 0, we get to, so this value function v0 belongs to that function space. So this function space, maybe just kind of write it as a bit more formally, theta. So this is our function space. So this definitely belongs to F. Now I want to compute V1. Suppose I want to do it exactly. So at k equal to 1, I have reward plus gamma times p v0, which would be r. what is the problem here? So, okay, so let me simplify it. So I need to have v of 1x being R1 essentially, which is 1. V of 1 of, sorry, this is x1, this is x2, it should be 0. And if I write it, but v of 1x1 is equal to theta, so theta 1, and this is equal to theta 1. So do you see the problem? So theta 1 should be 1, but theta 1, the second equation says that theta 1 should be 0. So which one we have to find? We have to compromise. We have to find a function, a theta, that minimizes that distance. So if you want to do it according to this kind of loss function, we are essentially, we have to solve minimization of, okay, where can I write? Maybe I write previous page, yeah. Well, maybe it's easier to try it. So we have to find a minimum of theta so it would be theta minus 0 squared plus theta minus 1 squared. So we find a minimizer of that. And I think it makes sense by symmetry that the minimizer would be half. So this one, now this value function belongs to that function space, but it is not correct for any of those states. And now we apply it again for the next iteration, and something might happen. Is there any questions so far? Okay, so maybe let's see. Yeah, I think it's a good point to have a break. So here I just mentioned that this procedure might diverge. So it is kind of important to know that if the value function space is not rich enough, this constant, depending on the behavior of MDP, the procedure approximate value iteration might diverge, or it may not diverge. So I guess that's one point I want to say. I don't know for this specific example. So I think it might be kind of good exercise if you try to see what is the behavior of it. So that's one thing I want to say. Maybe in this lecture, I'm not talking about RL, but in next lecture, hopefully we cover it. But you can see that this procedure can be kind of converted to an empirical one or data dependent one by modifying this TV of. Okay, so if this step requires a model, T of V pi, Vk. If we don't know the model, we can't compute it. But if we have data, we can have an unbiased estimate of that T of Vk. If you recall before, so we say, for example, in Q-learning or TD method in general, we substituted something like this, T of y, say at pi x, we substituted with some reward plus gamma of v of x prime when x prime comes from the model. And then we had this idea that conditional expectation of it would be exactly the same as what we have. So we can find using only data, using only data, we can compute an unbiased noisy version of this T pi k here. And that would be one of the kind of approaches to make it a reinforcement learning algorithm. And you see and maybe it's good to think about, you see that a method like a deep Q network, DQN, which is one of the kind of the important methods in basic methods also in deep RL, is basically doing this procedure using some neural network. Okay, so I think that's the other thing I wanted to mention now. We can have a break, maybe for 5 minutes. Now it's 2. We can start at maybe 2:05, and then we continue. Okay, let's continue. So I talked about approximate value iteration. Let's talk about some other methods for finding an approximate value function. So this idea is called, the next idea is called Bellman residual minimization, or Bellman error minimization. And I'm going to talk about its population version. So what is the idea? The idea is that, recall that from several lectures ago, that if you find a V such that V minus T pi V is equality, so, or V is equal to T pi V, or V minus T pi V is equal to 0, then that function should be V pi. That's the property of uniqueness of the value function. If we have a function approximator, however, we cannot guarantee that. We may not be able to have this equality exactly. Instead, what we might have is just have an approximate equality. So we will have V is approximately close to T pi V. And here V again is kind of restricted to belong to some value function space. So piecewise constant, decision tree, neural network, or whatever. So in general, if we restrict value function to some function space, we may only have an approximate equality. And as what we did in previous part for I guess both different previous methods, we need to convert this approximate equality to some kind of way that we can quantify it by using some distance function or some norm. So a common one is to use the LP norm with respect to some distribution mu. And again, this distribution, the choice of L2 squared error is the most common one, but one could use others. So here maybe this is a good to mention that mu, you will see that how it appears when we go to the RL setting is often the case that mu is related to the distribution of data that we have. So that this mu would be, for example, the distribution that is generated by the behavior policy that is used to collect data. But here at this level, we are talking about kind of the abstract level. So here, the procedure is, okay, we take the LP norm of V minus T pi V, and then find a minimum of value function within some value function space. And that would be our approximated value function. So this also can be written because by Bellman, as a Bellman residual. Like recall that Bellman residual was defined by exactly this T pi V minus V. So we have that. We get it that it's equivalent of norm of the Bellman residual. So that's why it's called Bellman residual minimization. So it's minimizing the norm of Bellman residual, which we called Bellman error before. So that's why you can also call it Bellman error minimization. But I think it's more common to call it BRM, Bellman residual minimization. So this procedure is called Bellman residual minimization. And you can also do the same thing with action value function. And instead of V here, have Q. So if instead of V, you have Q, you get a Bellman residual minimization for action value function. Okay, is this clear so far? Okay, perfect. So it kind of, I guess if you compare it with approximate value iteration, it is interesting because this procedure is, like approximate value iteration was an iterative procedure. We find some VK, we apply TVK and get to the next VK plus 1 and do it many, many times until we converge. So it was a iterative procedure. Here, however, this is kind of formulated as an optimization problem that if we can find a solution in one shot, given that optimization is not necessarily easy, but suppose we can do it, solve the optimization problem, in one shot, it gives us the value function for that policy. Maybe one other thing that is, I mean, I wrote it here for TPy when, for computation of the value computation or policy evaluation problem. You could write it for T star, but it is, I think, maybe more common to use it only for value function policy evaluation. And then on top of it, we might have some kind of policy improvement iteration. So this would be part of a policy iteration algorithm or approximate policy iteration. One other note that I have to say, I mean, at this stage, it doesn't matter, but when we want to use data, doing this procedure is not going to be easy, or better to say, if we do it, just the trick that we used before, just substitute the reward plus gamma times v of x prime instead of t pi of v. So if we substitute it with r plus gamma v of x prime, this would not result in a correct algorithm in some sense. So the loss function would be biased in a way that I'm going to talk about. So exactly this procedure is not used in practice or should not be used. I mean, people use it, but they shouldn't. There are some modifications of it that solve this issue, but I may talk about them later. Okay, so this is BRM. So let's have some kind of geometric intuition of what it's doing. So BRM, so at each step, so for each value function in that value function space F, so for example, V1, when we apply the Bellman operator to it, we get this other point, which might be outside that value function space. So for different points, we have different solutions or TPy V's. And here, this Bellman residual minimization is trying to minimize the size of this kind of vector, maybe you can think of function, the residual Bellman residual function, and find a V that has the minimum distance. So I think, yeah, I guess I mentioned this, that if F is a set of linear function spaces, its geometry is can be shown as a plane. So it's a hyperplane with a subspace spanned by features phi. So this is that hyperplane here. I mentioned this part before. Okay. Just imagine that, suppose that there exists a V such that V minus T pi V is equal to 0. So it means that, well, we start from this point, we kind of get to the same point. So I've showed some little distance between them. But this distance, suppose, is equal to 0. If that's the case, and if we assume that that distribution is positive everywhere in all states, it means that, well, this distance is 0, so V minus T pi V for all states should be 0, which means that V of x minus T pi V of x, or is equal to T pi V of x for all states in that state space. Which means that, as we had seen before, this means that this is satisfying the Bellman equation So its solution, what we have found, would be T V pi. But this is only under condition that this V minus T pi V is equal to 0. In general, it is not. So in general, the error is not 0. So the minimizer is, what we find is not the value function V pi. But it is still has some kind of nice approximation properties that I'm going to talk about. But before there, is there any question? Maybe ask here or in the chat, or is everything clear?
So if the error is not 0, the minimizer isn't necessarily unique, right?
Well, okay, so yes, not necessarily unique, yes, but it depends on, I guess, the function space and how it is. It may or may not be unique, yes.
Okay, I guess earlier that's what I was kind of trying to ask. So if you, depending on the initialization, if there are multiple solutions, you could converge to a different one.
Right. Okay, so I guess there are two things. One is that if you minimize some function or loss function, when we talk about minimization here, I talk about global minimization. But when you talk about initialization, it is basically saying that probably you're getting stuck in one of the local minimums. So
yeah,
initialization matters if you have a kind of neural network and you talk about local minimum. But here, when I talk about argmin, I'm talking about global minimum, which in most cases, but not always, we assume it is unique. So I think there are two issues. One is that what happens because of the optimization procedure, and that of course depends on the minimizer. And the consequence for us is that, well, if we're in practice, we want to minimize this thing, we use a neural network, we don't actually find the argmin in it. We just find some other point, which is not argmin.
Yeah, makes sense. Thanks.
But here, I assume everything, like the minimization can be done exactly, which is not going to be the case for neural network. So, but this is kind of this level of abstraction that even if we find the minimum, how good it might be.
So, sorry, I had a couple questions on the last slide. So I was wondering if you could explain what mu was again. I kind of forgot.
Mu is a distribution. Yeah. Let me try to. Mu is when I define a norm here. So here I'm talking about different, like in all these loss functions, I talked about LP mu, for example. Mu is the distribution that is coming here in the definition of this norm.
Oh, okay. Those are the weights?
The weights on different functions, yes, different states. Okay,
the weights of different states. Okay.
Yes. So okay. So let me this example, like this case, the usual integration is the case that the weight in all states is the same. But sometimes you have a case that you have more emphasis in some regions of the state space. And that mu is essentially reflecting that, or that's mu here. Maybe another way to think about it is that is closer to what we do in machine learning, maybe. If this is the state space X, suppose I collect a lot of the distribution of data points are concentrated in one region. So many data points are here, a few in other points. So effectively, maybe they're coming from a distribution like this. So here, if we have such a distribution, when we talk about a norm, This is basically saying that we focus more on this region, and the amount that we focus depends on that distribution, mu.
Got it. Okay, yeah, that makes sense. And the other question is it's probably pretty basic, but in the value, or when you're looking at the Bellman residual,
right?
The x prime, that's a state that we're also sampling from the probability transition kernel.
Yeah. So where did I?
It's not the state that maximizes the.
Right.
Okay.
So I think you are referring to here, right?
Yeah.
So here, yes. So basically, I need to expand this. This is kind of just a, but x prime was essentially, x prime would be these points. That is generated from a random sample from p pi condition x. So here, if I want to, yeah, maybe if I just want to write this down, it would be, let's try to zoom it. So hopefully it fits. So I'm talking essentially about v of x minus r pi of x plus gamma p pi of, say, d of x prime conditional x of value at x prime. And then the weighting would be according to distribution mu. So that's the loss function that we have. And what I'm saying is that, so this thing that I talked about, replacing it, means that replace this whole part, replace this part by some reward plus gamma times v of x prime, where x prime comes from the next state for that particular x. And x prime comes from, as I wrote before. So this x prime is only for that particular x. If I change x, as I'm doing here through this integration, that would be different x prime. And you will see that later when we want to convert this to a kind of RL algorithm, we don't have so here, instead of mu, we will have a bunch of data points coming from state space. And instead of x primes, they would be, x primes would be the next state after each of those points.
Okay.
Yeah, so that's a good question. Just requires some expansions. All right. Any other question? Okay, perfect. So in general, the minimizer error is not zero. So the minimizer v is not the value function v pi, but there is still some good approximation properties. And I'm going to talk about two of them. One of them we have already seen before, which is in one of the earlier, I guess on lecture 2. So we had this upper bound that basically says that if we have v minus t pi v and take its supremum norm, it provides an upper bound on the supremum norm of v minus v pi. And there's a multiplication of, or division by y minus gamma 2. So this is essentially saying that if we find an a function v that has a small Bellman error. This is the Bellman error, the right-hand side. Then it provides an upper bound on the closeness of that function to the true v pi that we want to find. So this means that the Bellman error, or the norm of the Bellman residual, is a surrogate loss. That instead of minimizing v minus v pi, which if we don't have v pi, we cannot minimize it. And recall that in the first method that I mentioned, assume that there's an oracle that gives us v pi, or maybe we can use a Monte Carlo estimate to find it. But suppose we don't have any v pi, we can still use Bellman error and minimize this quantity, which does not depend on, there's no v pi in it. So it is enough to know compute the Bellman operator on some function, any function v, and then find a v that minimizes it. That would be an upper bound on what we actually care about. So this would be a kind of example of what we call surrogate loss. So, and previous kind of argument that I had here, that if there exists a v such that this quantity is equal to 0, is compatible with this bound. Because if the right-hand side is, if it is 0, then the left-hand side would be also 0. But in general, the right-hand side is not 0, so it is just providing an upper bound. But minimizing an upper bound is kind of pushing down the left-hand side, which is the quantity that we care. So what are the issues here? One issue is that Supremum norm is very conservative and in some sense unforgiving, in a sense that even if there is one state that our error is large, then this upper bound says that the Bellman error, or the Bellman error would be very large according to Supremum norm. So maybe just kind of give you an example. Suppose I'm showing you value function. The true value function is, say, this one. And suppose I find a function that kind of follows it very closely, except at one point. Everywhere it is close, except at one point, at one state x. The Supremum norm of this difference is going to be essentially determined by that single point. So if you have billions of points or a continuous state space, you have infinite number of points. In all points, you are accurate except one point of one very small region. This Supremum norm says your error might be actually very large. And then the guarantee that I can provide on the Supremum norm again, Supremum norm of your quality of your approximated value function is also going to be not very small. So that error might be large. So this is one issue. And this is not necessarily an issue of, like, there's nothing wrong with this upper bound. This upper bound is correct. It is just Supremum norm is a too strict a requirement to have a small value for. So I guess that's one thing. The other thing is that in machine learning, we often minimize something like L2 norm and not Supremum norm. Because computationally it is easier in many cases, but also because when we have data points, we often cannot really guarantee that our function would be accurate in every point. We can only say that in average, in expectation, our function is accurate. So if you give me random points, I would be a good classifier. But there always exists some small points that I might be a very bad classifier. For classification or for value function is that I can only give you an average with respect to some distribution. I am a good predictor of the value function, but not every point. And maybe just mention that as kind of footnote or remark that there are methods in machine learning that can provide guarantee on the supremum norm of the errors, but they usually require more assumptions on data. So they usually assume some kind of having data distribution, having a density that is bounded away from zero, which means that if I have a data point, I mean, this is a bit tangential, but might be interesting. So if I have an input space X and I have a distribution that comes from this data is generated from, the distribution should, I mean, can go up and down, but the minimum distance should be larger than zero. So if, for example, I have an example like distribution that is like this and goes to zero and then goes up, in this region that I have a zero sample from, I cannot, no machine learning algorithm can provide any guarantee on the accuracy of its prediction because there is no data there, unless you make kind of some assumptions about the data generating process. But if you don't make any assumption on data generating process, only have distributional assumption, then if the distribution, the density goes to zero, then we cannot provide supremum norm guarantee. Okay, anyway. Okay, so here what we have, so an upper bound for the Bellman error and related quality of value function, but it's in supremum norm. We want to have something that's a bit more, it's a bit nicer and kind of incorporate something like performance in average instead of worst case performance. And I'm going to show you results. We are going through the proof that when the distribution mu, or the distribution that we talk about, would be a station distribution of a policy pi. So in that case, we can provide very similar upper bounds. Okay, so what is the station distribution of a policy? The intuition is this, that the station distribution of a policy is a distribution that if you start from, at the next time step, you would be at the same distribution. So if your states at time one starts randomly from a station distribution, you follow the policy for one step, you get to state time two, and you get samples from x2. The distribution of that samples, the distribution of it, would be the same as the distribution of x1. If you are in that situation, then your distribution has been the station distribution of a policy or invariant distribution. So I guess the explanation that I gave you is more like invariant. It doesn't vary as time goes on. And I guess you shouldn't confuse this stationary distribution with stationary policy that we had before. I mean, they are in some sense related, in the sense related that things do not change, but that was a different concept. Okay, so let's talk about it a little bit, see what are the properties of it. So this is basically what I mentioned already. So we initiate the state at x1 according to some distribution rho, and the agent follows pi, gets to x2 as usual. Then the distribution of x2, what's the distribution of x2 in the next state? So I think we had it before, something like this, that the distribution of x2, or the probability of x2 being in some set x, is essentially depends on the probability that state agent has started at state x, which was rho, and the probability that from that state x, it goes to state set b. So if this is the state space, this is set b, the probability at x2 being at that state is the probability that from all different points, with p pi we go there, and the probability of each of these states is rho of pi. Or if we have a countable state space, we can also write the probability at state x2 being y, one particular y, is the probability that we start from state x, and then from x we go to y according to the p of pi. So that's essentially one expansion of the distribution. So nothing is about station distribution. Station distribution comes to the picture when this probability of p of x2 being y is the same as probability of x1 being y. So if probability of x1 being y is the same as probability of x2 being y for all y's in the state space, then that rho, if that's the case, that rho would be the invariant or station distribution. Okay, so.
Sorry.
Sure.
In the previous slide, we are talking about the stationary distribution of policy pi. So we are basically assuming that the stochastic distribution of pi is stationary across different states. But here we are doing integration based on the transition dynamics of the environment rather than the policy, right?
No, here I'm like in this slide, I'm not talking about any station distribution yet. I just talk about if we start at rho, what will be the distribution at x2?
Yeah, but that distribution is about the environment transition dynamics rather than the policy.
No, well, okay, so so this is not station distribution of policy. This is this. I guess I understand what you're saying. This is the distribution induced by the policy. So we choose action according to policy pi, and then at next state we go at x2. So here, like here, this is p of pi. When I have it, it means that I'm choosing action A1 according to some distribution, according to some policy pi, and then I go to x2 according to dynamics.
So basically, it includes the marginalization of the action. Okay.
Yeah.
Okay, I see.
Yes, p pi policy is inside it. But here, it is about the dynamics of the Markov chain that is induced by following policy pi. So this is not the distribution of pi or actions, this is distribution of states by following pi. So dynamics should be in the picture. Okay, so station distribution of policy pi. Okay, so here I want to talk about the case that if the distribution of x1 and x2 are both rho, or maybe I use rho pi here. Okay, so that's, so rho pi, so it's if it's station distribution, the kind of the definition that I had was that the distribution of x1 and the station distribution of x2 should be the same. So if the distribution of x1 and x2 are both, say, rho pi, we say that rho is the station distribution induced by pi. And by induction, it would also be the distribution of x3, x4 up to infinity. So if you are starting from this station distribution, we will always, our states will always have the distribution of station distribution. And that's why it's stationary, because it doesn't change. So let's just kind of derive a relationship for this station distribution. If x1 and x2 are both at the station distribution, rho pi, then what we have, the consequence is that the probability of x1 being at y, for any state y, is the same as probability of x2 being at y. So this can be written as, okay, p of x1 equal to y, which is by our kind of definition, is rho pi of y. That should be the same as the distribution of x2. What was the station distribution of x2? We had it from previous slides, so exactly what we have here. for the case of okay. Or here for the case, general case. So this distribution of x2 is this summation of p of rho pi of x, because we started from, at state x1 started from rho pi, and then transitioning to y according to probability of p pi of y condition x. And this is averaging over all possible x's with some probability we go to the same y. So this is the same y from different states we are getting to it. And the probability of each of these states is coming from rho pi. And the transition probability is p of pi. So this means that we have this identity in the middle. Or if you want to write it in the general state space, it would be rho of pi for set B is equal to rho of x. So that should be rho of pi of x. And then times p of pi going from state x to set B. So that's the kind of property of it. If we have a countable state space, then we can write these things in a kind of nice matrix form. I think we had this before, but if p of pi, we can denote it by n matrix, n being the number of states. And we define the matrix in this way, that p of pi, x and y, column and row x, column x, row y, would be probability p pi, x going to y. So if we do that, and we write it in the kind of matrix, the previous summation, write it with this notation, it would be rho of pi of y summation over x of p pi of x and y times rho pi of x. And this should hold for all y's. So this, I think you can think about it that in matrix notation, it would be rho pi transpose would be equal to rho pi transpose times p pi. I guess it just think about like writing summation in form of matrix. So this basically also means that the distribution rho is an eigenvector of matrix P. This is left eigenvector because usually when we talk about eigenvectors, right, for matrix A, we have AU is equal to lambda U. So this is right eigenvector, but we can also have U transpose A is equal to U transpose. We use different notation. We may also have V transpose A is lambda V transpose. So this is more like in this form. Or likewise, we can think about it as we take transpose of both sides, we can get the p pi transpose times rho pi is equal to rho pi. So then it means that this station distribution rho pi is either we can think of it as the left eigenvector corresponding to eigenvalue equal to 1 of matrix p pi, or right eigenvector corresponding to eigenvalue 1 of matrix p pi transpose. So that's a kind of property of it. I don't think we use it. We don't use it in this lecture. Maybe we use it later. But this is interesting to know. Some other property of station distribution is that under certain condition on the Markov chain, or Markov decision, Markov chain essentially, the Markov chain that is induced by pi converges to rho pi, the station distribution, no matter where we start, no matter what is the initial distribution. So for example, for any mu, any station distribution mu, what we have is that if we start from mu and follow pi for k steps, so which is shown here by p pi to the power of k, which is the case if you have in matrix form, actually matrix taking p pi, matrix p pi to the power of k, that converges in certain sense to rho pi. So this means that if you start your some corner of the room and you follow policy, eventually you converge to station distribution of that policy. There are some conditions, of course. So for example, if you are in a room, there are two rooms, there is a door here, but the door is closed, and you start from here, you never gets to the right-hand side. So there are these issues like this, and I just put them in kind of conditions. But we have this kind of general property if everything is nice. Okay, so now I want to provide something like what we had before, the error bound that we had before, that was for the supremum norm, but show it for the station distribution, or with respect to station distribution. Okay, so what is the result? Is that if rho pi is the station distribution of p pi, then for any value function, and any p, we have that the difference between v and v pi, L1 norm of it, but measured according to rho pi, so that's the weighting of it, is upper bounded by the difference between v minus t pi v, so Bellman residual, the norm of it, what norm? Any p norm, but again weighting according to rho pi, the station distribution, divided by 1 minus gamma. So this is the property that holds. So if the Bellman error or Bellman residual has a small norm with respect to station distribution, you also have a small norm of the difference between v and v pi. And this, you can compare it with the supremum norm-based result that we had before, but instead of supremum, we have now L1 norm or LP norm. The left-hand side here is always L1 in the result I'm showing you. The right-hand side can be L1, L2, or anything. Okay, is this clear? There is a question. So the question is that there's no guarantee that station distribution exists, right? We are just assuming it does for this proof. So here we assume it exists. There are some conditions that it exists. So okay, so I can't remember the exact condition that we need, but it's a very general. So usually we have station distribution is well defined if the Markov chain is not strange. But there might be the cases that it doesn't exist. But the condition, I should check. I think if the state space is, okay, I should check. I mean, if the state space is countable, then everything should be nice as long as we have, I guess we always have an eigen vector corresponding to eigenvalue equal to 1. It may not be unique if there's a degeneracy. For general functions, in general state spaces, continuous ones, you require some conditions. I guess a good point to take a look at it is the book by Main and Tweedy. There's a Markov chain book that they have that provides other relation, but I need to check them to see what are the conditions. Okay. So we assume that it exists, often exists, but maybe there are some kind of cases that it does not. So how do we show it? So in this kind of proofs, so we start from what we want to show and then try to upper bound it. So v minus v pi. And then see that we want to get something that is related to v minus t pi v. So this kind of the proof technique is add t pi v there, or construct v minus t pi v. So what we have is that for any v minus v pi is v minus t pi v plus t pi v minus v pi. So essentially added and subtracted these two terms. And now I factorize or decompose them to v minus t pi v and t pi v minus t pi v pi. Okay, so I guess the first term is clear. So these two terms is this. Why do I have t pi v pi here?
Fixed point.
It's fixed point, yes, exactly. Because v pi is equal to t pi. So I just want to make it similar to t pi that I have here. So I just wrote it in the other form. And the second term, I just evaluated the state x and try to simplify it. So t pi v of x minus t pi v pi of x is, we have a reward part, but they cancel. So what remains would be gamma times integral of p pi dyx times the difference between v of y minus v pi of y. Is this clear? So that's what we have. Okay, now I start from this equation 9, take absolute value of both sides, and then use the update form of the second term, and then integrate with respect to rho pi. So these 3 steps. So just when we look at the left-hand side. So essentially what I'm trying to do here is take absolute value of this and take integral with respect to d of x. So d of. And I do the same thing for the right-hand side. And the result would be what I'm showing you here, which is absolute value of v of x, v pi of d rho pi of x, the integral of it. And this is, remember, this is the left-hand side of the upper bound that we want to prove. So the left-hand side is already in the right form that we want. Is upper bounded by v of x minus t pi v, absolute value of it, and then integrated with respect to rho pi of x, the station distribution. So this is the first term. And then the second term would be gamma times this absolute value of the term that we got in the previous page. So p pi dyx, v of y minus v pi of y. So the absolute value of it, and then weighted according to the station distribution. So we have these two terms. Then by Jensen's inequality, I am moving the absolute value inside the integration. So I'm moving this absolute value that is here to inside. So I compute it here instead. So the result would be, I guess maybe kind of simple case, intuitive case would be like, say if I have a distribution p of x of f of x, just anything, the absolute value of this is smaller than P of x, f of x, d of x. So what I'm doing here is essentially that. And that's a result of Jensen's inequality, if you want to prove it. Okay, so by Jensen's equality, we have the left-hand side is upper bounded by, again, the same first term, plus gamma times d rho pi of x, p pi dyx at vy minus v pi y. Okay, so what should we do here? And let's focus on these two terms. So we are saying that we're starting from state x with distribution of station distribution, and we go to the state y according to the model. So what is the distribution of y?
Stationary?
It is a station distribution, right? Because if you start from stationary, we follow one step of the policy, this distribution stays the same, the stationary policy. Okay, so because rho pi is the station distribution, the second integral on the right-hand side can be simplified as, okay, so that's the integral, can be simplified as just these two terms would be equal to rho of pi of y. So it would be integral of rho pi of y times vy minus v pi of y, which is written here. Here I just changed the notation from x to y, but maybe it would be more clear if I kept it as y. This is at the next state, but it doesn't matter because I'm taking integral over the whole state space. Okay, so that's great. So what we have all these things. So this term that we have is equal to our norm, v minus v pi. What norm is it? Is it L2 norm? There it is, the answer. It's L1, yes, exactly. So it's L1 with respect to distribution pi. The same for the other one. So this is also the norm, but this is norm of v minus t pi v. So it's a norm of the L1 norm of the Bellman residual. And the other one, okay, so the last term, we just showed that in this next slide, that this is again equal to L1 norm. And we had one gamma there before. So we get L1 norm of v minus v pi is equal to L1 norm of the Bellman residual plus gamma times L1 norm of v minus v pi, which means that if I rearrange it, I get the result for p equal to 1. So if I move this to the left side, I would get 1 minus gamma v minus v pi is equal to the L1 norm of the Bellman residual. And then by Jensen's inequality, again, I can show that L1 norm is a lower bound for any other LP norm. So I get the result for any LP norm. Is this clear?
Sorry, I thought there was a nested integral for the first equation, but I guess it's equivalent anyways.
Are you talking about this step?
Yeah.
Right. Okay. So what I did is, so there's a nested integral, but okay. So what happened here is that it's a bit crowded. So we have rho pi, and then there is absolute value outside this integral, and then we have p pi dyx of vy minus v pi. By this identity, I move the absolute value inside to get to this point. So this second term would become gamma times integral of d rho pi p pi dyx of this absolute value here. Is this clear so far?
Yeah.
So this is again two integrals in some sense. Like there is one integration over x, the other integration is over y, but I just show with one integration. Is this okay so far?
Yeah, all good.
Okay, and then I guess next step I use this stationary property to convert these two integrals, if you wish, to just one integral over the rho of pi. So here the integration is over both x and y, but then because of stationary property, the effect of it at y is essentially the same as x being from stationary distribution. Okay. Any other question?
I guess I'm still wrapping my mind a little bit around the rho pi of x. So if you integrate d rho pi of x over all of x, does that evaluate to 1?
Mm-hmm. Yes, it does.
That would evaluate to 1. Okay. And then if you integrated over dx, oh, okay. So that's the, okay. Okay. I think.
Is it clear?
Yeah. I'm just trying to visualize it. So this is kind of like the probability density function.
It is a probability distribution. It might be density or not, but it is the distribution of, it's a distribution that if the agent follows, it would not change.
Mm-hmm. Okay.
Yeah, so maybe, yeah, I guess it's good to think about it, go through the notes, see if it becomes more clear or not. I mean, it's a new concept. And if it is not clear, then we can try to find a solution for that. Okay, so that's good. Okay, so I think next I talk about another method called projected Bellman error, which is going to be many different methods, it turns out, would be somehow related to this, even like temporal difference learning. You can think of it as a kind of variation of doing it. So I'm not going to talk about it now. And if I have time, so I wanted, I guess value function approximation is important. So I think it's good to have a good coverage of it. I wanted to finish, but I guess I was a bit my expectation was unrealistic. So next I'm going to talk about this and then go into the learning part. Hopefully learning part wouldn't be too difficult because everything we just substitute Bellman operators with samples, more or less. I mean, there's also some subtle details. And then maybe I try to prove the convergence rate for one of these algorithms for approximate value iteration. I don't know, I like to do it, but it may mean that I need to skip or not cover one of the topics at the end. We'll see. Maybe I don't cover bandits much. So I guess the things that I want to cover for sure is policy gradient methods. And I think it's very good to have model-based reinforcement learning. Bandits are interesting, but I'm not going to talk about it beyond multi-arm bandits. So it's a way to do exploration, exploitation by doing something a bit smarter than epsilon greedy. But epsilon greedy is okay enough for RL at least. So we'll see, maybe I skip that.